To introduce our presenter today, Dr. Britt Fawcett. Britt is an ecosystem scientist, certified professional of erosion and sediment control, and leadership in energy and environmental design accredited professional. Britt earned his PhD from the Odom School of Ecology at the University of Georgia, and he currently directs research and technical services programs for Filtrexx International. Britt coordinates research, design, and training services for the stormwater and organic materials management industries and serves on technical committees and boards with ASTM, GRHC, CCREF, and IPA. In 2008, he was awarded the annual USCC Clean Water Award. Britt has authored numerous peer-reviewed and popular press publications and popular press articles, 2 books, federal and state specifications, and has been awarded nearly $500,000 in research grants. Please welcome Dr. Britt Fawcett.
Thank you, Kristen, and thanks everybody for attending the webinar today. Just to reiterate a few of the key points before we get started that Kristen mentioned. I do like to hold all the questions until the end. My very last slide will have my contact information on it with my phone number and my email. So if for some reason we run short of time and we don't get to answer one of your questions, please jot down my information and you can contact me afterwards. Or if you feel like the question that you have is more appropriate to engage with me one-on-one, maybe on a specific project or specific site, or maybe a more lengthy conversation or question, feel free to reach out to me and we can have a chat that way too. If you're new to our webinar series, welcome. We do this monthly, as Kristen mentioned, and you can get on our website and see the other webinars that we offer. And I greatly encourage you to look at that and to sign up for one of ours. You'll notice that if you have seen those, or if you've tuned in the past, you'll notice that that these often build on each other. They have some familiar themes, but they often build on each other. And using compost-based BMPs. If you're no stranger to our webinar series, welcome back. And we're always happy to have you for as many as you want to attend. So let me jump in here. I always like to give a little bit of an outline of how we'll move through the the presentation. I always like to start by really kind of laying the foundation of really how we're working within stormwater management and how compost really fits into the equation. And to do that, we really have to understand the really this movement or paradigm shift from gray to green infrastructure. You'll often hear people call it low impact development or LID. These things are, these two terms, you'll hear me use them synonymously, green infrastructure and low impact development. They have a lot of similarities, but they actually are a little bit different, and I'll touch on that later on in the presentation. From there, I'm going to talk about how compost really fits into green infrastructure and how we're using it for stormwater management. And I'm not going to insult anybody's intelligence here and tell you how compost is being used for vegetation establishment and vegetation sustainability, which is a key component of stormwater management. But where two of the key aspects of where we're really making great strides really over the past 5 to 10 years is in reducing stormwater volume, as well as improving stormwater quality through biofiltration mechanisms. So I actually have another presentation or another webinar that speaks directly to reducing stormwater volume, and by doing that we actually reduce pollutant loading at the same time. I won't talk about it anymore in this presentation, so if you're interested in that aspect, please attend one of our future webinars. I am going to talk about how we're using it for filtration and biofiltration aspects to improve stormwater quality. I'm going to share with you all the different applications or best management practices of where we use compost, and I'm going to talk about really some of the key, no pun intended, but some of the watershed research that's helped us understand the performance of these recycled organics and compost in these applications, how they perform, sometimes how they perform compared to other management practices. And it's really an applied-based research. I think you'll see that it's really important to us at Filtrexx when when we do research, we engage with universities and federal agencies to publish the research and make it publicly available, which is very important to us, and publish in peer-reviewed scientific journals, but also have it in a very applied research context. So we're taking this information and not only just understanding how these things perform and why they perform, but also evolving it into design and engineering information as well. So not only can we use it for decision making, but we can also use that information in site design in a very practical way. So that's a really important process for us. I'm going to share some case studies with you that really kind of drive some of the points home, and of course we ought to have some question and answer too. The values you see on the screen here, you're probably no stranger to if you have been working in the stormwater industry for even a short period of time. But there's a recent report that came out that said over 850 U.S. cities and municipalities have either outdated or under-designed stormwater management infrastructure. According to the U.S. EPA, about 3/4 of all Americans live near a polluted surface water body. If we were to get on their impaired water body list that they maintain on their website, the U.S. EPA, for TMDLs, or total maximum daily load designated water bodies, we'd see that we're actually approaching about 50,000 water body segments distributed across the United States right now. And if we are, another study has said that if we were to add up what we pay as a society to clean up our water due to poor or ineffective stormwater management, we pay about $44 billion per year. If you've seen me speak before, there's a very good chance that you have seen some version of this slide before. I love the way that it visually represents what happens as we change our land use patterns from natural systems like you see on the left to greater and greater development and land disturbance and urbanization and more impervious surface. So there's lots of studies now that show that the more development you have in the watershed, and really the more impervious surface you have in the watershed, the more stormwater you're going to have, and consequently the higher the pollutant loads. There's a direct link between volume of stormwater and pollutant loading, and of course the higher the pollutant loading, you generally have more pollutants that get into receiving water bodies or surface water bodies. And that's really what this is showing you, and it's also showing you that we're actually breaking the water cycle in the process. So you see under the natural systems there's very minimal pollution. The color coordination shows you that there's minimal to no surface water runoff or storm water, and basically what happens is we get rid of these natural materials, these natural systems like vegetation and canopy cover and grasses and natural levels of organic matter in our soils. What happens is we reduce the ability for to recharge water back up into our atmosphere in the form of evaporation and transpiration. This is actually regional climate change that's actually occurring here. We talk a lot about global climate change. This is actually regional climate change. When we take down our vegetation and reduce our biomass, we actually reduce the ability for this moisture to go back up into the air and come back down as rainfall. So we're actually warming and drying on a bioregional basis when we do this. We're also reducing the ability for water to infiltrate and percolate down into the soil profile and recharge our groundwaters and our surface waters. And what happens is when we reduce each one of those natural systems in the natural hydrologic cycle, we have more and more surface runoff, and when we have more surface runoff, it carries a lot of pollutants along with it, and you see that here in the graphic. So you can look at the red as more stormwater in these developed watersheds. You can also look at them as more pollution as well, because they are inextricably linked when we have more impervious surface in the watershed. As I mentioned, the U.S. EPA says that about 3/4 of all Americans live near a polluted water body. If you were to take a deeper dive and a closer look at what they have on their website, these are the top pollutants that they have listed: coliform bacteria, a range of metals. This is copper, cadmium, chromium, nickel, lead, and zinc. Generally, we find most of these coming from our building structures and our roads and parking lots and highways, mostly coming from transportation sectors. Nutrients, nitrogen and phosphorus, so mostly macronutrients. Fine sediments, the ones that really stay in suspension once they get into a water column, that lead to high turbidity and suspended solids. These are going to be your clays or your fine sediments. And then last but not least, petroleum hydrocarbons. So not only are these the items that the top pollutants that we see listed for impaired water bodies, they're also the top pollutants that we find in our urban and suburban runoff as well. So no surprise there that what we find, the pollutants in our stormwater, are the very top pollutants that we find polluting our water bodies. If we look at some of these source areas to figure out where the problem areas are and really what we need to target, as I already mentioned, a lot of the metals are coming from parking lots, highway, streets, and rooftops. We also get a lot of hydrocarbons coming from the same areas minus the rooftops. Golf courses and lawns are actually the leading sources of nutrients getting into our water bodies, and pet parks, believe it or not, are one of the leading, if not the leading, source of fecal coliform contamination in our urban and suburban areas, stormwater originating from those areas. Who cares the most, or who's really paying a lot of attention to this? So anybody that has a national pollutant discharge elimination system stormwater permit, okay, that could be a land disturbing activity or a construction site. For most areas in the country, that's anywhere that's disturbing 1 acre or greater, they must have a stormwater permit. Now, generally, they're only targeting sediment in those applications and not some of the other pollutants that I mentioned. But industrial stormwater permit holders and MS4s or municipal separate storm sewer system permit holders often do have to target not only sediment, but also a lot of the other pollutants that I mentioned earlier. And all of these entities, it's very possible, depending on their SIC code and the size of their municipality, that they may have a stormwater permit. I've also put in here animal feeding operations or concentrated animal feeding operations. Now, a lot of them don't necessarily have to have a stormwater permit, but they are source areas for often for fecal coliform as well as nutrients and potentially sediment as well. And these have been priority areas for the USDA as well as the landowners who operate these facilities to do more in targeting these pollutants and keeping, either reducing the sources themselves or keeping them on site, not letting them get into surface water bodies. Some of the key priority areas, and this is probably pretty intuitive for most folks, but anywhere that's a known fishing area, particularly when they have a commercial value like trout and salmon bearing water bodies, anywhere where there's already been identified an endangered species, anywhere where the water has already become even slightly eutrophic, meaning low dissolved oxygen levels, probably too much nutrients getting into those water bodies, leading to algae blooms. Anywhere where we actually recreate, whether it's a beach or some sort of shorefront where we're doing boating or fishing or swimming, and of course if it's already been designated as an impaired water body or on the TMDL designated water body list. I think it's helpful to look at some other stormwater treatment practices or technology or broad technology groups or categories as we begin to talk about using compost-based biofilters. So the compost FiltrexX is itself a biofilter. It's also a passive treatment system. So we rely on natural means to filter. We're going to talk more about this momentarily. We rely on natural passive flow characteristics. So it's just gravity flow. There's no energy source here. There's no pushing water through these systems. They often are compared to active treatment systems, which generally often do rely on some sort of energy source and some concentrated flow of material through a device, often what we call a vault or a black box, to actually move polluted water or stormwater through these systems. Often there's a chemical treatment to that as well as the energy component. So you can see how these the downsides of these types of systems is that they rely on an energy source, which can be problematic depending on where the project is located, as well as chemical treatment. to treat these systems, and they can only handle certain volumes too and flow rates, so they can be very restricted based off those, where these passive biofilters actually can be designed and sized in a multitude of different ways to fit a particular site. And then last but not least, most folks are familiar with the old stormwater pond, where we're collecting and containing stormwater, whether it's for retention or detention purposes. Oftentimes chemical treatment will go along with these stormwater ponds, but they're either meant to allow for sediment deposition to occur or contain the stormwater so we can treat it, or just to hold it indefinitely on site and to prevent it from really migrating in off-site or getting into other surface water bodies. If we were to take a closer look at some of the key elements of low impact development and green infrastructure. So low impact development is actually a design theory and a design concept that has been around quite a bit longer than green infrastructure has. So the strict definition of low impact development is the post-development hydrology will mimic the pre-developed or the natural site condition. So it really gets into site hydrology. It really deals really specifically with the site, whereas green infrastructure has often been called the U.S. EPA's Low Impact Development Program, and that agency really coined the phrase green infrastructure, and it really gets into the idea of supplanting our gray infrastructure, our pipes, our inlets, our channel systems with a different type of infrastructure, meaning green. So it's vegetated, it's natural, it's organic, but it really takes a watershed approach as opposed to just a site approach. It does include the site, but it moves into the watershed, and it also gets into capture and reusing of both rainwater and stormwater, where low impact development generally has not gone to that level of capture and reuse. But if we do look at really the key tenets of LID here and how it works, these are really the top 7 design elements of low impact development. Interception of rainfall, transpiration of captured transpiration through plant materials, even surface materials, infiltration down into the soil, evaporation from soil surfaces or organic materials put on the soil surface, designing soil roughness into the system to slow down surface runoff, and also flow path disruption to actually slow down runoff once it occurs. So there's a lot of restoring the natural water cycle here, slowing down runoff, getting water to move into and through the soil, and then last but not least, biofiltration. Okay, and that's where we come in. So if you look at this graphic I have here, the arrow that's 35% surface water detained and infiltrated, what's happening in this natural process is rainwater and or stormwater is moving down through that organic matter and topsoil layer, and it's either going down through the subsoil and recharging that groundwater, or it's moving just below the soil surface, what we call interflow or subsurface flow, and will move laterally down to that surface water body. And either one of those processes, whether it's the subsurface flow or recharging of groundwaters, it actually gets naturally filtered in this process. Okay, so this is the concept that we have used to develop the compost FiltrSoxx technology. It's really what we call, you've probably heard the term biomimicry. It's design inspired by nature, and that's really what we're doing here. So we're using this concept, but now of these natural organic materials, but now we're putting that concept above ground as opposed to only relying on infiltration of rainwater or stormwater down into the soil profile. And the advantage of that is that we can put this biofiltration technique just about anywhere we want on a land surface, and we can put it in the flow path. We know in land disturbance and through urbanization that surface water runoff number, which is quite low in the graphic here because it's a natural environment, that's going to be much higher, and there's going to be pollutants associated with it. So if we can get that natural biofiltration behavior and processes in that flow path, we're actually not only mimicking nature, but we're actually getting that high performance process in the areas that need it most. going a little bit farther into the type of media that we use here. So at Filtrexx, we use compost for all of the products and practices and technologies that we use and develop. And actually, I'm going to show you a list here of all the different best management practices that we use in stormwater management, but they all use one of two types of compost. The first one is what we call a filter media. Sometimes we call it a biofiltration media. It's specifically designed for optimum filtration of pollutants and also hydraulic flow or passive flow of water through the system. We don't want to create a dam. We don't want to create an obstruction. We're not relying on just flow restriction and sediment deposition here in order to improve water quality. That's what a straw wattle and a silt fence does. We actually want water to passively move through these systems and filter it. Now, we are restricting flow to a degree because we are putting something in the flow path. Remember that from the LID design, but we are relying on filtration mechanisms as well. We're going to talk, this media here is what we're going to focus on and the practices that use it throughout the rest of the webinar. The growing media, which you see on the right, is designed for optimum water absorption. Okay, so you can see how we're sort of trying to biomimic these natural systems of water absorption and absorbing rainfall and both stormwater. It's also, you can see that it's has some larger particles to it as well, larger than most compost that you would probably buy at a garden center in a bagged product. So we're actually designing surface roughness actually into the material. Pretty easy to do that. And it's also designed for plant growth, so we want to grow vegetation with this material as well. Now, I have a whole another webinar that really talks about this type of material and why we use it and how we use it and how it performs and what it does. So if you're interested in that, that subject matter, please tune in to one of our future webinars on that, and you can get a much deeper dive into those applications and some of that research. So all of these use the filter media. Okay, it's that very coarse media, and you can see a variety of the applications on where we're using it, from sediment control to check dam applications, slope interruption devices, sediment traps. We also use these in this media in bioretention systems and biofiltration systems where we're looking at combining vegetation as well. As an example, if you look at the lower right-hand corner, this is a designed biofiltration system to filter pollutants coming off of a large parking lot. So this is a list of stormwater management BMPs. There's 24 here, and you're probably noticing the ones on the left are for construction activity stormwater management or erosion and sediment control. The ones on the right are really post-construction stormwater management or low impact development or green infrastructure type practices. Now, I've highlighted the ones in red font that use this really coarse compost filter media. It's biofiltration media that relies on passive filtration to do its job. The ones in black really use the growing media. And so if you're interested, if you recognize these practices, these are all generic terms. If you're interested in these practices that are in the black font, those become the subject of one of my other webinars. So please tune into that again if you're interested. I don't spend a lot of time talking about the SOX specifications because this is really something you can dig into outside of the webinar. If you've seen our specifications or you're familiar with them, they actually are very detail oriented. If you compare them to other manufacturers or vendors that have specifications on their practices or their technology and their product, you'll notice that ours are extremely long, and that's actually by design. So we find that we look at our specifications also as an educational opportunity, because we realize for a lot of folks, they may be coming to our systems for the first time, or they're trying to understand how it works or why it works or where it works, or what the limitations are, maybe what the inherent advantages are. So it's almost like a one-stop shop of how you use these things and where, and just to have a greater understanding, because oftentimes when folks are specifying or engineering or designing with our products, we don't have the opportunity to engage them in a webinar like this, or or to have an educational opportunity. So we take that advantage, and then we also have a summarized version as well. But a couple of the key elements of those that really make these unique are the different size diameters of the compost filter sock, and you can see here ranging from 8-inch all the way up to 32-inch. We actually even offer a 5-inch diameter filter sock in some limited regional locations. The weight is actually also one of the unique inherent advantages here, ranging from 13 pounds per linear foot up to about 200 pounds per linear foot. So, yep, you've guessed it, these are heavy practices, and that's actually a really good thing. So once these things are put down on the ground and installed, they have they're actually really stable. They're not going to float. They're not going to move if they're installed correctly, and it takes quite a bit of hydraulic pressure to move these things or to knock them around, and that's a good thing. We like that. They also have a very high flow rate. I've talked a lot about the passive flow characteristic of the technology. I'm going to talk more about this in a moment here, but this gives you an idea of the hydraulic flow through rate through the systems, ranging from about 7.5 gallons per minute per linear foot up to about 30. So this is pretty high for any type of filtration device, particularly passive biofilter. And then the mesh opening sizes. A lot of folks ask this question of why the mesh opening sizes or what type of mesh is appropriate. So we found in our research that the optimum range is between 1/8 of an inch to 3/8 of an inch. Really, if you get larger than that 3/8 of an inch, what happens is you're not doing an optimum job of holding in the material as you're transporting the compost filter sock or putting it down on the ground. And of course, you want to hold in the recycled organic biofiltration material here. You get below 1 inch opening size or aperture size in the mesh, and it begins to behave more like a silt fence does, where it just becomes more about the mesh or the fabric itself and not really about the compost filter media or what's inside, which is actually the workhorse of these systems is what's inside, not the containment system. The only purpose of the mesh in these applications for us is to contain the material and to be able to easily handle it, transport it, and put it where you want it and contain it. There's not a unique performance aspect of the mesh itself, and we don't want it to be. We want the organic material to be the performance mechanism. I've talked a bit about this already in talking about biomimicry, so I'm going to move beyond that. But what I do want to spend a little bit more time talking about is really how and why the compost filter media works the way that it does. So it's what we really call a three-way filtration system or biofiltration system. There's a physical component here, and actually the physical component just relies on very typical filtration elements and design. There's actually not a lot that's unique here, but the key aspect is using and specifying the right particle sizes, and by doing that we not only allow water to move through the system, but we create these pore spaces to trap a variety of particulates and sediments. And so there's other types of technologies that do this. You don't want the compost filter media, again, to be too small, because then you're just blocking the flow and everything, and you have very little design capacity through the system, and it actually is not a passive filtration device once you do that, once it becomes just a blocking mechanism, and I'm going to touch on this again in a moment. What begins to make it really quite unique is the chemical component, and we know that organic matter, and we know that compost has the ability to, and even specifically humus materials have the ability to absorb soluble pollutants that are present in stormwater. In fact, US EPA has advocated for many, many years to use compost in polluted soil environments to tie up pollutants in polluted soils, like in brownfields and even Superfund sites, to remediate those soils. And it just so happens that some of the very same pollutants that we find in polluted soils we actually find in our urban stormwater as well. So it's good to be able to use those. Now we're just using them not just in the soil context, but also in a water context as well. So examples of these pollutants are metals, hydrocarbons, ammonium, nitrogen, all adsorbed to compost media quite readily. There's a biological component as well. We know that a mature compost has a very broad diversity of beneficial bacteria, as well as very high population numbers. It's not the same ones that you find in the thermophilic composting process. It's very similar to what you'd find in a very healthy soil ecosystem. But in fact, the numbers that you would find and even the diversity may even be much greater. In fact, the numbers are much greater in compost than we typically see in a very healthy soil ecosystem. And these beneficial bacteria can degrade and transform a lot of the pollutants that we're trapping in the system itself. So there's actually a bit of bioremediation going on here in situ in the ground. Very much the same concept that we have with bioretention systems, constructed wetlands, that type of idea. There's a fourth component here as well, and I'll only talk about it as opposed to typing it in here because it's more of an option, and that is phytoremediation. So we can design specific plant materials into the system that will grow within the compost Filtrexx, which will take up into the biomass of the vegetation some of the pollutants that we're trapping here. And by the biological aspect and the phytoremediation aspect, what's happening is we're giving the filter material, the biofiltration material, a greater capacity and ability to then filter more pollutants that may be coming in the storm water. So very unique aspect, and it really makes the whole system function longer and have a greater capacity to capture pollutants. I touched on this in the last slide, but I want to really drive this point home because I think it's really one of the key take-home messages. So we find that if you're new to this, the concepts that you're thinking of using compost in these applications is using the type of compost that's what some people call a coffee ground type compost, or some folks will call it a 1/4 inch minus if you're in that industry. But it's a very fine compost, and it's typical to what you would find in a bagged product at your local garden center. Key take-home message: that is not what we're using here, and you see the visual representation here in the upper right-hand corner. And there's actually a lot of research, published research, that's gone on to evaluate and develop the optimum particle size of this composted material. So it is a composted material. It's gone through the same process. The way that we get those larger particles is at a commercial or an industrial facility. There's a large screening screening equipment or process that separates the finer particles, which typically go into these bagged products, or they're used in agriculture, used in landscape projects, and the larger particles that are screened off, what we often call the overs, it has been historically discarded or been used back in the process, where we're actually using that material for these a lot of these filtration applications. And to the specifier, the end user, this graphic helps to sort of exemplify why this is important. So if you look at the bottom, particle sizes ranging from about a 1/4 inch to 2 inches. As those particles increase in their distribution, what you see here is the flow-through rate, or the passive flow-through rate through the system, increases, but the filtration ability goes down. This is no different than any type of design for any type of filter that most of us use in our everyday lives, from a water filter in our fridge or our sink, or even a pool, or even an air filter in our truck or our car or HVAC system at home. What happens is we design larger apertures or pore spaces, and water or air moves through at a faster rate, but we have a lower ability to trap particulates or pollutants in the process. Now, if we were to reduce those apertures or those pore spaces by reducing the particle sizes of the media, now we're going to move to the left-hand side of that scale. What you see is the flow-through rate goes down to ultimately 0. And what that means is we're just blocking all the runoff or water that comes to the device. We don't want that either, because what you're going to get is overflow fairly quickly. You're going to get reduced design capacity. You're actually going to need more product because you're going to be overflowing at a more rapid and persistent basis. And consequently, this is what straw wattles and silt fences are designed to do. They have very little to no flow-through rate. So as soon as water comes to them, it begins to back up. You get hydraulic pressure, which can lead to pushing or undercutting of these devices, and then pretty rapid overtopping as well. So the thing that actually makes them function is actually the thing that makes them fail as well. But you also see that the filtration ability goes up, and it's not that the true filtration ability goes up. What this actually is saying is that we're just blocking everything, so the water and any associated sediment or pollutants that may be present. But of course, we're going to get some sort of overtopping quite quickly, and so we don't really want that to occur either. So there's this optimum performance zone here in the middle that that has both that specifies mostly these larger particles, but some of these medium-sized particles as well. And this representation that you see here in the graphic is consequently what you'll see in compost FiltrSoxx specifications throughout the country, from basically every federal agency that has the ability to specify or have a guidance document for this type of application, to just about every Department of Transportation or state EPA that also has the ability to specify this type of practice or technology. So now you're beginning to see that these filtration, excuse me, these filtration devices or biofiltration devices really have got to use this filter media. And there's no better example than the photo in the upper right hand corner here, and that is, you look at this inlet protection sock around the storm drain, and the first thing that most folks think about when they see this photo is that we're trying to keep sediment and particulates outside of that storm drain, really any type of trash or pollution that is greater in size than the openings of that storm drain. That's actually the secondary goal there. The primary goal is to continue to allow the stormwater to get into that drain. So there's a lot of impervious surface here. Presumably there's a lot of traffic and automobiles and truck traffic. The last thing we want to do is to divert runoff away from that storm drain. It was put there for a purpose, and dam up water or create a situation where there's potential hydroplaning and an unsafe environment for traffic and for people. So where it can ultimately, unfortunately, lead to property or personal injury, and that's the very last thing that anybody wants. So we need to allow that water to continue to get into that drain, and secondarily do a better job than that grate does of keeping particulates and pollutants out. I'm going to share some research with you here for the next section of the presentation. Excuse me. So this is a study that was done at San Diego State University. They're one of the only labs in the country that actually had the ability to test the performance of erosion and sediment control materials using a standard ASTM methodology, really designed for these types of practices, originally for erosion control practices. And you can see here the difference in performance for compost FiltrSoxx versus silt fence versus straw wattles. This is another study. This has been published in the Journal of Soil and Water Conservation, performed by the University of Georgia, comparing two different diameters of compost FiltrSoxx to a wood chip filter berm and a straw wattle. Two things came out of this study. One, the higher performance of the compost FiltrSoxx compared to these other organic practices for sediment control, but also no improvement in going to a larger diameter sock. So this is a little counterintuitive. I think a lot of folks think if you want more filtration, go to a larger sock, and that's not necessarily the case. What this is showing us is that the main reason to go to a larger device here is just to handle greater drainage area. or more design capacity to handle runoff and accumulation, not necessarily to improve water quality. Now, there's a theme developing here that I want you to tune into here. So the study at San Diego State University showed about 77% removal efficiency of sediment for the compost FiltrSoxx. Here we're at just over 80%. This is a study at the USDA Ag Research Service showing suspended solids reduction for the FiltrSoxx at about 78%, and also comparing it to silt fence and reduction of turbidity as well. So what I've done is shown you 3 studies from 3 major research institutions distributed different areas around the country using different soil types, which means different sediment types, different methodologies, different rainfall intensities and durations and flow rates, and they're all showing a fairly consistent removal efficiency across these studies and these published studies of around 80%, a little bit below, a little bit above. So I think a trend is developing here where folks are utilizing this about the 80% removal efficiency level of sediment and suspended solids for this type of practice, assuming that it's designed correctly and specified correctly. We're seeing that in these studies. So we partnered with some scientists from the USDA Ag Research Service at their research headquarters outside of Washington, D.C. To further develop the compost FiltrSoxx as a management practice. So to really begin to look at it as not just a sediment control device, which is how it was originally designed and developed, but more as a true biofilter. So beginning to target more of these stormwater pollutants that I've been talking about, the soluble fractions of these pollutants. It's important to know and recognize that in the construction activity context, we only target sediment because that is the largest load, largest pollutant load, and we've taken away vegetation, we've disturbed soil, so we have a very high degree of sediment, and conventional wisdom says other pollutants that are present will attach themselves to sediment when it's in such a large volume or mass or load like that. So if you trap the sediment, you'll also get these other pollutants. On the post-construction context, this isn't true anymore, actually. So presumably you have quite good stabilization, whether it's an impervious surface or whether it's vegetation. And studies show that between 50 to 80% of the total pollutant load in the stormwater in those areas in that post-construction context are in the soluble form. So they're not attached to sediment, they're not attached to particulates. So a regular sediment control device like a hay bale or a straw wallet or a silt fence isn't going to do much good in those types of applications. So this is really the idea behind working with the USDA and the scientists there to further look at the compost FiltrSoxx as a biofilter. So one of the things we wanted to do was to specifically target and evaluate and develop the practice for fine sediments, for nitrogen and phosphorus, for harmful bacteria, for metals and hydrocarbons. So the very same pollutants that the US EPA has identified as the leading pollutants in our surface water bodies and our stormwater. These are some results in taking the suspended solids fraction that we're removing through the compost FiltrSoxx and looking at how the particle size of that sediment and how good of a job this biofilter is at removing these materials. So what you see here is over this 30-minute runoff event, the compost FiltrSoxx, and really the information that I'm sharing with you here is actually what has led to the EnviroSoxx technology. So a lot of the information I'm sharing with you is the data and the information on our EnviroSoxx technology for those of you who are interested or familiar with that product. So the clay, we removed about 60% of clay. So clay is really the finest particulate fraction of sediment. You can see the particle size in blue down at the bottom, really between 0.01 to 5.7 micrometers, and then silt at about 75% removal removal efficiency, which is the next smallest fraction of sediment that leads to a high degree of suspended solids or persistent turbidity in a runoff column. We're removing about 75% of that. This actually, let me go back, this actually flies in the face of conventional wisdom a little bit, because this industry has historically said if you want to target these fine sediments, you can't really do it through filtration or really biofiltration, passive filtration mechanisms. You have to either do it through long sediment deposition times, which means containing the stormwater and allowing the water, the sediment to settle out over a long period of time, i.e. think of a stormwater pond, or you need to have some sort of chemical treatment to flocculate these very fine sediments to make them come together into larger pieces. Now they're heavier and more dense, and then they'll fall out of the water column. We often do that in ponds. We often do that through other types of treatment technology. So it's either through containment and deposition or through chemical treatment. Both of these are really expensive, can lead to very large land area footprints. So the idea that we can actually do this through small footprint passive biofiltration mechanisms is actually pretty unique, and it's actually really pushing the thinking behind how we target fine sediments in a new direction. Soluble phosphorus, by adding the additive to the EnviroSoxx to target phosphorus, we're actually able to get up to 90%, just over 90% removal efficiency for soluble phosphorus. For nitrogen, in the form of ammonium nitrogen and nitrate nitrogen, we're actually able to get between 25 and nearly 35% removal for both of those soluble forms of nitrogen species. Bacteria, in targeting both E. coli and total coliform, we're actually able to get in the 99th percentile of removal efficiency with the additive in our EnviroSoxx technology. Looking at metals, and I apologize because there's a lot of data on this slide, but there's something pretty unique here with how the what we call our MetalLoxx additive works with our EnviroSoxx. So the metals you're looking at here are the very same metals that we talked about earlier on in the presentation that we find are persistent problems in our stormwater: cadmium, chromium, copper, nickel, lead, and zinc. What we've done here is separated out the removal efficiency for the metals that are in the soluble form or fraction versus those that are in the particulate or sediment bound fraction. So we know there's a pretty long history of scientific published research on how the compost FiltrSoxx practice or technology works for removal efficiency of sediment, even fine sediments like suspended solids and turbidity. So we thought that if there was metals that are bound to particulates or sediments, it's probably going to have a pretty decent removal efficiency. But the true worth or value of these biofilters, or any stormwater filter for that matter, is their ability to target the soluble fraction. It's a lot tougher to target these soluble fractions. It takes a lot more, really a lot more in development, and they're a lot more valuable consequently, because that can be the highest percentage form of these particular pollutants. So what you're looking at here, I've highlighted in red the soluble versus the sediment bound, and then the total. So if you're just interested in the total removal efficiency, that's the bottom row there, starting with 73% for cadmium, moving across to 53% for zinc. The soluble fraction is the top row in red, starting at 72% for cadmium, ending in 57% for zinc, and then just the sediment bound fraction is at 77%, you see there. So pretty unique here, and it's important when you evaluate these types of practices and technologies to really separate this out and to look at the soluble removal efficiencies for the pollutants. We found that the EnviroSoxx and compost FiltrSoxx practice works really well for petroleum hydrocarbon removal. We see in the 99th percentile for motor oil and diesel fuel removal. We actually even tested it for gasoline, and we're about 55%, almost 60% removal efficiency for gasoline, although in all honesty, although I have a picture here with some gasoline sheen on in stormwater. Gasoline often evaporates pretty quickly once it hits an impervious surface. So unless you have a spill or a puddling effect during a stormwater event, it's usually not as much of an issue as these other two are that are more viscous and usually stick around for quite some time. I wanted to share a case study with you, which I think is pretty cool. So we had the opportunity to work with the City of Chattanooga. They're a municipal separate storm sewer system permittee, and we're out of compliance for their MS4 stormwater permit back in 2007. You can see an aerial photograph here of a 5.5 acre parking lot where they store and service a lot of their city vehicles. You can see in the table here they were out of compliance for chemical oxygen demand, suspended solids, and oil and grease. They asked us to come in with a solution, a compost-based biofiltration solution to help them get back in compliance. And really that's what you see in the photograph to the right. So you can see the pipe, which is one of the major outfalls for the site. You can see probably the fence line barely in the upper portion of the photograph. That's actually their property line. So once the stormwater passes that that fence line, it's off their property, and it needs to meet certain stormwater effluent limit guidelines as defined by the state of Tennessee. So we put in this system, which was a compost Filtrexx baffle, which you see here going perpendicular to flow, as well as a vegetated SOX system as well leading up to the baffle. And back in June of 2007, you can see the reduction in concentrations for these three pollutants. We actually got them back in compliance at that point, kept them in compliance. I have data here through 2009, but actually kept them in compliance through 2012, at which point they actually tore the system out and wanted to put in something else that for educational and demonstration purposes they wanted to evaluate. Otherwise it was the system was still working well for them. You can see the reduction or removal efficiency ranges here in red at the end of the table as well, and they were actually so pleased with how well it performed and how easy it was to install and maintain and use that they actually educate other municipalities in Tennessee on how to use this type of system for MS4 permit compliance. Something new I wanted to share with you guys before we wrap up is we're actually now beginning to, or more recently, we've taken this EnviroSoxx technology in the compost filter media and put it basin inlet filter. So what's pretty unique about it is it's basically using the EnviroSoxx or the compost filter sock media in a replaceable filter cartridge, which you see here depicted in the photograph. It has a flow rate of a maximum flow rate of about 35 gallons per minute. The filter does. The system itself, which is housed in a bucket system, and you can see some of the overflow apertures around the top portion of the bucket there, is designed to have an overflow of greater than 500 gallons per minute. And it's pretty unique. We offer this nationwide now, and it's getting a lot of interest for both industrial and MS4 stormwater permittees. Last but not least, I just want to touch on one of the key elements of why so many folks have become very interested in Filtrexx and the practices and the technologies and the systems we use, and it's because we really, all of our systems really do rely on biomimicry. That's really at the key, at the center of our technologies and our design thinking when we develop new products and implement them into the environment. We really truly call them a sustainable BMP or a sustainable management practice. You may have heard some of us use this terminology. It uses 100% recycled material, which is compost. It's biologically based organic material, so we rely very little to none, depending on the practice, on petroleum-based materials and products. It's often locally manufactured. This is one of the great sustainability stories of using compost. The U.S. Composting Council has said that there's over 4,000 composting facilities distributed across the United States. So as long as the material, the compost material is well composted and meets specification, this type of material can be procured in a lot of different places. And if you're getting it locally, not only are you supporting a local business, but you're reducing transportation costs, and you're actually using recycled materials that are most likely adapted to the bioregion in which they recycled. So you're actually kind of closing the loop at a community scale, and you're really following natural principles and ecological practices and food web principles when you do that. Not only are you reducing carbon footprint because you're not transporting materials and products from across the country or even shipping them from overseas like a lot of the products in this stormwater management category do or are from, but because you're keeping organic materials out of the landfill. Landfills are one of, if not the leading source of methane generation in the United States. It's a greenhouse gas. It's 25 times more concentrated in carbon or carbon dioxide equivalents than CO2. And just by keeping these organic materials, by choosing these materials, you're creating a demand to keep these materials out of the landfill, not only saving landfill space, but reducing carbon-based gases as well. So you're reducing carbon footprint that way, and also by getting these back into the landscape, a mature compost has during the composting process creates a stable form of carbon that once it's put on or back into the soil, that's also a form of carbon sequestration. So it is, we won't say it's permanently put there, but it's put there for into a pool for a long period of time. So you're actually taking that out of the atmosphere and reducing carbon footprint that way. So you can actually have a pretty profound impact on carbon footprint reduction just by choosing a compost-based practice. I've talked a lot about this, but they all these systems that we're talking about use natural principles. They mimic nature. They use biomimicry as their key design element, and whether it's rebuilding or protecting natural capital or relying on ecosystem services or enhancing ecosystem services in the process, these are principles that we all ascribe to, and it's actually part of the mission statement at Filtrexx. And of course, these things perform quite well. So there's a lot of published research now on the performance of these practices just for the application that they're intended to provide in terms of reducing stormwater or improving water quality, and that's really the key reason why we're choosing and using these things anyway and putting them into an environment. So with that, I've used the better part of the hour. I think we can open it up to questions, and of course here's my contact information if you'd like to talk at a later time or for a lengthier conversation. So thanks for your time and attention, and I think we got time for some questions.
Great. Thank you so much, Britt. We do have a few questions lined up. If you have a question and you're able to stick around, you can go ahead and type that into your dashboard and we'll address all of these. First question, how effective are compost sacks in addressing the new California IGP permit compliance threshold for various soluble pollutants like heavy metals?
Good question. They can be very effective. It depends on the specific site, of course, and the flow of the stormwater and the concentration and the loading of specific pollutants coming to the system. So it would be inappropriate for me to say, yes, use this technology and you're going to get in compliance. In fact, it would be pretty disingenuous for anybody to say that about any product or technology without knowing more about the site and what's going on. So, but what I can say is when those elements are known and the system is designed correctly, it can either help these permittees achieve compliance or in fact get them in compliance. So we advocate strongly for a treatment train approach. So there are no silver bullets in particularly in this industry. So just by saying yes, use this product and you'll get there is a bit disingenuous, although it does happen. but we really advocate for a whole treatment train approach to stormwater management for any site, and that goes for industrial stormwater permittees, MS4 permittees, and even construction activity permittees. You never see somebody just put up a sediment control device on a construction site and do nothing else, and then call it good.
Great. Okay. We have two questions regarding how the SOxx work in removing soluble iron and aluminum.
Good question. We have anecdotal information and project-specific information where we've worked with industrial stormwater permit holders where we've seen positive reduction of both of those elements. Generally what we find is the removal efficiency is not quite as great as some of the others that I've shown you in the research here, and it's partly because the mechanisms that sorb those elements are not as the absorption strength is not as strong. So although you may remove you may or you will remove some of those elements, the strength is not as persistent there, and that's true for a range of metals. So they can actually become desorbed in some cases, or if an element or a metal comes along that has a greater affinity to adsorption to our system, it may release some of the iron or the aluminum because it has a lower affinity for those. Now, if it's attached to particulate or sediment, we're going to remove a very high percentage of that. So I'm just talking about the soluble fraction there. So yeah, I hope that helps.
Okay, great. What do you think the mechanism is for removal of COD? We often have COD leached from compost and wood treatment areas at landfills.
Yeah, I think it's that's a good question. So what we generally see the COD elevated COD is generally is often, not only, but generally from persistent of nutrients, generally nitrogen and phosphorus, getting into those waters. So from an organics recycling facility, you do have the ability in the storage of the organic wastes and in the process of the organic wastes to have nitrogen and phosphorus in the runoff. And I'm not divulging any secrets here. So the BMPs need to be put in place to not only management-wise, but also potentially treatment-wise to handle that. And you'll see that nationwide. What's different is that once the materials go through the composting process, not only have nutrients become more stable, but we actually select out for those types of elements in the compost filter media. So we generally use only yard waste based green waste materials, which are already very low in those nutrient profiles, have a very high carbon to nitrogen or carbon to phosphorus ratio, and then obviously as it goes through the process, the composting process, they become more stable, and then we're actually removing the fraction of the compost that actually in some cases may have the ability to provide or contribute nitrogen and phosphorus, and that is the fine particles. So you've seen throughout the presentation that we use only the coarse fraction. So not only is it already a high carbon to nitrogen or carbon to phosphorus ratio, or another way to say that is very low nutrient profile compost, we've actually taken out those materials that contribute to that as well. And when you do that, we've actually seen that these materials not only can move from potentially being a source or a provider to actually being a net reducer of these materials. Also, the natural additive that we blend into the EnviroSoxx is also specifically designed to target nutrients and COD reduction as well.
Okay, great. Are the filter sacks typically filled on site?
No, they're not. So the socks are, whether you're talking about just a compost filter sock or you're talking about EnviroSoxx, they're generally made at a regionally based manufacturing facility and put on a pallet and then shipped to the site. They can be made on site, that is an option, but generally it costs more to do that. The advantage to that is that sometimes you can get into areas that may be more difficult. The disadvantage is that often it's more expensive to do that. The equipment needed to do that is very expensive to operate and to mobilize. And you also probably increase the risk of not meeting specification when you manufacture on site versus at a known facility that specializes in doing this and in the media and making the materials, and that's all they do.
Okay. What's the best way of taking a water sample for analysis when using the EnviroSoxx and StormX products?
The first thing I would say is to follow the US EPA guidelines for stormwater sampling. They have a whole book and guidance document on industrial and municipal stormwater sampling, chain of custody, and analysis. So I more than strongly recommend reading that and following those guidelines, and consequently really just about every state environmental agency, state EPA, their guidelines basically say follow the US EPA document rather than creating their own. So that said, follow those, and depending on how the install is with either of these products, it may be difficult to get a water sample. It just depends on where you're putting it and how you're installing it and the shape of the ground, so to speak, and your access to that. And this is really no different than any other types of BMPs too. That I think the last thing you want to do is, if you're placing a BMP in the flow path of stormwater and there's not a known area where you can collect the stormwater, you don't want to start scraping up water off the pavement as a sample. That's against what the US EPA says for stormwater sampling. So if you know you have to sample after a certain treatment device, you need to take that into design, or take that into consideration when you're designing with any type of BMP, including our own.
Okay, we have a couple more. Thank you everyone for sticking around for this portion. How important is design capacity when using your product as a passive treatment filter?
It's very important. There's a couple ways to interpret this question, whether from a flow capacity of the water or from the pollutant removal capacity. And we have design information for the flow capacity. As far as the pollutant removal capacity, the only way to be sure of when you're reaching that capacity is to do testing. So if you're already a permittee that is required to do testing, you'll probably know when that time is. If you're not, that becomes more difficult because you're not actually doing that testing. And so as a general recommendation, we'll tell folks who are looking for a specific calendar date, depending on their site and the amount of stormwater and the level of pollutants, could be anywhere from 3 months to even 2 years. And if you include vegetation in the system, that can actually increase the longevity and capacity as well. So.
Okay, great. I think this is the last question we have lined up. I've heard you sell a stock that is biodegradable, for example, useful as post-construction BMPs. How many clients use this, and is it used in the EnviroSoxx?
I couldn't tell you how many use it. I don't really have access personally to that information, but we have had a cotton mesh material available for quite a few years now, and we more recently have what we call our enhanced cotton mesh, which actually lasts a little bit longer. So yes, we do have a biodegradable mesh. It's available all over North America. It is widely used. Some state agencies are actually requiring it, and many state agencies are moving either rapidly or moderately in the direction to require it. We generally don't use it for EnviroSoxx because our customers in that area haven't actually been asking for the biodegradable sock for that particular application. We find it mostly, most folks want to use it in the construction activity context, where it's only going to last a certain time period during active construction, and then the mesh will go away. And on these sites, they're generally not going to go back and remove the practice. They just want it to go away. Where on our industrial and even MS4 stormwater permittees, they're generally pretty active on the site, and so they want that mesh to last a certain time period. And then when the filter, it's more about the filter itself, not really the containment system. So when the filter is done, they're going to remove the filter, and want to know that when they do move it, that it's still in its contained mesh. So I won't say that we don't get some requests for biodegradable sock in the EnviroSoxx for the EnviroSoxx, but it's quite minor at this time.
Okay. Those are all the questions we have lined up here. Thank you everyone for sticking around in a really good Q&A here today. I'll be emailing your certificates of attendance. Feel free to contact Britt with any questions. His information's on the screen, and I'll also include that when I email the certificates, so have that handy. And again, you can visit our website to see the upcoming webinar schedule. Britt, do you have anything else to add?
I don't. Just yeah, thanks everybody for attending today. Hope you'll tune into one of our future webinars. I can tell there's a lot of interest. A great Q&A here at the end on the EnviroSoxx, and I think a lot of folks on the webinar would get a lot out of our low impact development webinar on how we're reducing stormwater volume with compost-based BMPs. And of course, when you're reducing volume, you're also reducing pollutant loads as well. So please look for that one and tune into that one in the future. Thank you.
All right. Great. Thanks everyone. Have a great week.